We have seen in the previous module how the allocation of the slots are done in position auctions, and we mentioned that they are done in the decreasing order of the product of this bid value and the estimated value of rho I, that is rho I hat. And why is that a reasonable thing to do? We are going to discuss that in this module. So what the allocation decision has to do is to decide who gets which slot. So if the allocation is given by this number, so this vector A, which is denoted by A1 to AN, where AI actually means the slot that has been allocated to player I. We have already assumed that there are more slots than the number of players, so therefore all that matters is that who gets which slot. So A1 means the slot that is obtained by player 1, and so on. So given that allocation, the value of an agent is going to be the following. So because it is player I has been allocated this particular slot, it gets the position effect of that slot, and then the estimated value in this from the point of view. So this is a point of view of the bidder. So they are going to allocate that with respect to this rho I hat, which is the quality effect of this ad, and this is the true type of player I. So this is essentially the expression for the valuation of player I when his type is theta I and the allocation is A. Now the natural candidate here is to use the efficient allocation. The sum of the valuation that is getting maximized is one possible way of allocating this slots, so that the more valuable slot goes to a more valuable bidder. Now what we are going to claim here is that when you do the allocation of slots in the way that we have discussed before, that is a rank by expected revenue mechanism. So what is this rank by expected revenue mechanism? Is that you have this rho I hat multiplied by the BIs, which is the bid, and sort all the bids with respect to in decreasing order of this, and then keep on allocating those to the higher slot. So the player who has the highest value for it, he or she gets the first slot, the second highest gets the second slot, and so on. So this claim is saying that if you do it in that way, it is efficient, and it's an if and only if condition. And the idea of this proof is very simple. What you are trying to do is essentially you have a multiplier. So you have a position effect, so P of J, and you are multiplying this rho I hat comma BI of player, and you are trying to take the sum of all these things. So this is the expected revenue that you are going to earn over all the slots. And we also know that this position effects decreases as the slots go from 1 to m. So therefore it is essentially a weighted maximizing the weighted sum problem. You are actually trying to maximize the weighted sum of a certain set of values, and if you put more weights to the larger value, you are going to maximize this sum. That is essentially the whole point of doing this rank by expected revenue mechanism. So therefore what is being done is actually efficient. That is going to solve this problem, the sum of the valuation problem, because you already know that there exists this decaying order of these PIs. Now if you look at the problem of solving this allocation, the slot allocation problem is essentially a sorting problem. You are just taking their bits, multiplying that with the rho I hats, and then just sorting it. So it is computationally quite tractable. Now once the allocation decision is done, we need to define the payments, because we are actually running an auction. So the very natural candidate to make a DSIC is the VCG mechanism, and indeed this is used in some of the social media platforms like Facebook. You might also ask the question that why we need the VCG mechanism, because it is maximizing the social welfare, but maybe the search engine's objective would be to maximize the revenue. And as we will see later in this course, that the optimal mechanism, there is little that is known about the optimal mechanism for multiple objects, and that is the reason we do not have a very precise answer of what will be the most appropriate mechanism if we want to maximize the revenue. While for social welfare maximizing, we do really know this VCG mechanism, and that can be applied. As we said before, the actual implementation in Facebook or other social media might be different from what we have actually discussed here. So we are only going to give you an abstract notion of how this auction can be done. For the position auction in VCG, so we have the bids, which are, you can think of this as the as same as the theta I hats, the reported type of player I. And we can also assume without loss of generality, because all the things that we are going to do is essentially anonymous. It does not really matter how you relabel these agents. So we can assume that player 1 is the one who has the highest product of this row I hat and bi. So, and they are decreasing in this order, right? So whenever we say that player 1, we are already assuming that he has the highest product of these two terms. So therefore, by the principle before, it is quite obvious that the ith slot should go to the ith agent, because they have this sorted order. And similarly, we can define the allocation of the slot except agent I to be the argmax of the sum of the valuations when agent I is not present, right? This will be useful when we calculate the VCG payment. Now what is going to happen, so there is certain simplification that is possible here. So all these agents are sorted in this order. So if you just remove one agent, so let's say from this list we are just removing agent I, then the sorted order remains the same. All that happens is the I plus 1th agent has now got the ith slot, and every later agent has actually got promotion to one slot above, and that is the only change that will happen when you remove someone. So this allocation is really very easy to compute. It's actually the same sorted order removing that agent. So therefore it is also very easy to compute what is the VCG payment is. So you can do this calculation. All that you can see is that when you have the agent I removed, you still have the same j starting from 1 to n minus 1, but now the allocation has gone to this new agent, which is j plus 1, and that is essentially that is happening because of the removal of that agent. For in the original case, it was still the same. So the slot j plus 1 was going to this agent j plus 1, but here they got a promotion because of the removal of agent I. And all the other agents, all the other advertisers who are above agent I in the original allocation, they are cancelled out in both sides, because their position is unaffected. So you can actually do this simplification and find out what is the final payment for agent I, advertiser I, in this bidding game. If you look at the last agent, so this is true for all the agents except the last agent, because there is no j plus 1 in that case. For that agent, the payment is always going to be 0, because his participation does not change any of the other allocations. So therefore that agent will have a 0 payment. Now this is so you can think of this to be the total expected payment. Now we'll have to design the price for each of the clicks, and the way the clicks are designed is that we have taken two effects. One is the position effect and also the quality of the ad effect. These two terms are pi times rho I hat, and we are just going to divide that. So the expected payment that we have from this VCG, we are going to divide that, and this is going to be the per click payment that this advertiser has to make.